Hello, and welcome to a brief introduction to the Computational Engineering and Design theme of the Mechanical Engineering undergraduate course. My name is Alex Dickinson. I lecture on the Part 1 Design and Computing course and next year's Systems Design and Computing course. So what is design? Many people put different meanings on the word design, but for our purposes, design is where you will bring together all of the technical knowledge that you're going to develop over all the different specific subjects of your course and apply that to solve problems. Who does computational engineering and design at the University of Southampton? Well, you students do. All the examples I'm going to show in the rest of this talk is work that students have done. And the best design work is presented at our annual design show, and you can see all of it at the design show website with this link here. What you'll see with the Formula Student car, as well as many real-world machines, is that we bring together multiple disciplines, such as structures, flows, thermodynamics, heat transfer, materials, electrical systems, electronics and control, and a lot of maths. And in engineering design, we use these tools to help us solve problems in an efficient way. Now, most of you will have been aware about Formula Student, but of course we have design in much more varied machines. This is a bone lengthening device, which is used to gradually stretch someone's tibia over several weeks or months if they have a leg length discrepancy. Conventionally, the lengthening is done mechanically, controlled by the patient's parent often, with an Allen key twice a day, and it has a 200% complication rate if they try to lengthen it after it's healed a little bit too much, and often then that leads to a fracture. A group of final year students designed a hexapod system to control the lengthening direction much more precisely than was capable with pre-existing designs, and to lengthen the bone gradually over the course of the day. This project links biomechanics with a choice of materials so that the device can be very easily cleanable and sterilizable and corrosion resistant. Ability to support quite high structural loads as somebody walks around wearing the device, and therefore to minimize weight. Miniature mechatronics and control system, which is informed using an array of sensors to make sure that it's not about to apply a degree of lengthening that's excessive. And very importantly, part of a design like this is system interfaces that have been designed very carefully for the user. We can't just assume that something like this will only be used by mechanical engineers. It has to be accessible to all the different kinds of users, such as the patients and their family members. So why do we study engineering design? Engineering design is about applying processes to help us move from a problem to a deliverable solution in a systematic way. We need to learn about the problem that we need to solve, but we also feel pressure or enthusiasm to start designing and making solutions, so we need to balance those two tasks. If we try to learn all about the problem first of all, we'll invest a lot of time and energy, but potentially we'll run out of time to actually design the solution itself. On the other hand, if we start designing too soon, we keep learning more and more about the problem as we design, but we realize that we need to change what we're designing because we didn't understand the problem in enough detail at the beginning, and it becomes a messy process with lots of trial and error and extra effort which your boss and your investors might consider a waste before you get to delivery. Design thinking and the design processes that we use here let us approach the design in a more systematic way. We still use iterations to get towards the final answer, and we might even end up with the same result that we would have done with the messy process, but we're more likely to produce an optimal solution and to use less effort in getting there. Hans Haugley has a great blog which illustrates this with a teapot example in a very accessible way, and the link is there. So why do we link design and computing together? There are actually several reasons. Once we're developing our ideas, we often start with geometry, and ideally that's CAD geometry. We use computer-aided design because it gives us a perpetual design record. It's easier to change than hand drawings are. We can perform virtual assembly of multiple parts so that we can find design errors before it's too late to change them or solve them, and because we can make much smarter renderings which obviously impress our customers. The second link is in simulations. Our designs are rarely so simple that we can analyze them and evaluate their performance with calculations on paper. So we use highly computationally intense simulation processes for fluid flows such as computational fluid dynamics, CFD, and structural analysis with finite element analysis, FEA. Finally, once we start looking at how to truly optimize our designs and improve their efficiency, we need to run those simulations over and over again. We perform design of experiments to search the design space efficiently, and optimization to find the design which lets us fulfill our requirements with, for example, minimum mass, minimal fuel consumption, minimal manufacturing cost. So we take the results of our optimization, we perform design modifications, we might find new candidates, and then ultimately we return back to geometry where we update our design and reanalyze it. Ideally, parametric CAD lets us use simulations to run lots of very slightly evolving designs over and over again many times and gets us closer to the true optimum. One real attraction of the CED theme is that it's very flexible. It lets you concentrate on the fundamentals of design and the maths behind the computing while applying it to whatever area you're interested in. We have detailed FEA, heat transfer and CFD subjects, numerical methods and optimization, but then you can add specialisms for your optional modules from a whole range of areas, for example, automotive or aerospace, biomedical, sustainable energy, and all sorts of other areas. For one final example, another totally different project was the Breath of Life, where students' customers were respiratory doctors and pathologists at the University Hospital Southampton. They wanted to CT scan a human lung in greater detail than ever before to see the microscopic airway structures inside, so that we can learn more about lung health and disease. We have a range of computed tomography scanners in the MUVIS X-ray Imaging Centre downstairs in Building 5, which lets us image objects in micron resolution. It's a lot like a medical CT scanner, with an X-ray source and an X-ray detector, and the thing you're imaging in between, except here, unlike a medical CT scanner where the source and detector move around the patient, here the source and the detector are stationary, and we have our object on a turntable and it revolves inside the fixed source and detector. To perform this scan, the students had to design a chamber to support the lung with minimal movement, which would blur the images. They had to keep it cryogenically frozen, and they had to do all of this with a range of safety measures to prevent the highly volatile coolant from bursting into flames, or this chamber from releasing potentially biohazardous material, obviously with this scan being biological material. The chamber had to fit within the constraints of the scanner and allow the X-ray source to be placed as close as possible to the lung, because that's the way that you can maximize the detail that you can resolve in the resulting scans. We use these volume data to perform modeling with geometry based on real images instead of idealized models of tubes or flow structures. So for example, we might perform micro CFD on a model like this where we can resolve those micro airways. And as well as the CFD, obviously, you can imagine that reconstructing the data, segmenting it to extract this 3D geometry, the red part, and even rendering the results images are very highly computationally intensive tasks, which again shows how design and computing can go hand in hand. Now, this was just a brief introduction to computational engineering and design, and the team and I will be giving you a lot more detail on the fundamentals this year in the FEG 1001 Design and Computing course, as well as in SESM 1016, which is the Mechanical Systems Analysis module. My research team and I use these methods as well in our work developing processes for people who design personalised prosthetic limbs. And you can follow what we do on our Twitter channel here. And again, have a look at the Design Show website to see the kinds of projects you might go on to do, whether you choose to pursue the computational engineering and design theme or not. Thank you very much.